So when you take, if you have two separate functions, you can take their limits separately and add them, subtract them. You can pull a constant in the front. You can multiply them. You can divide them. You can take the power of the exponent outside of the limit. 7, just make sure we got this one down. If you take the limit of 5 as x goes to 3, what would that equal? 5. Just 5. And that has to do with the fact that 5 is a horizontal function. It's a horizontal line. So no matter what x approaches, the limit's going to equal 5. That's a constant function. And number 8 we use all the time because we're using direct substitution and plugging that value in. Same thing for 9 and 10 with the roots. We have another root property. Talk about direct substitution, which is what I've already discussed with limits. And then we get into what we call the squeeze theorem. Okay? The squeeze theorem, it hasn't come up yet on an AP exam, but it could, I suppose. So it's something that we want to actually kind of address. Really what it involves is it involves two functions that you know what the limits are. And then you have this other function that you know it's between the two, but you can't figure out the limit on its own. But if it's between the two, and you know the limits of the two on the end, then you automatically force the limit to be the one in between. Let me give you an example of this. Actually, I think it might be on the next page. Let me just double check here. Yeah, this one right here. Let's say we wanted to find the limit of x squared times the sine of 1 over x as x goes to 0. You can't just put 0 in because you get a 0 on the bottom of the fraction. But here's what you can do. You can kind of think about the unit circle again and say, what is the sine of any angle always between on the unit circle? What's the largest that a y value can be on the unit circle? A 1. And what's the smallest it can be? -1. So it's between 1 and -1. Okay? If that's true, then what must be true about the sine of 1 over x? It's between 1 and -1. Right? Now, let's do a little magic here, and let's multiply by an x squared. Both sides, all three sides, in fact, and we get -x squared and x squared sine of 1 over x and x squared. We've just created an inequality in which the function that we're trying to calculate the limit of is between two really basic functions, a -x squared and a +x squared. And you can see it on the graph here. In blue, that's the -x squared. In orange, that's the +x squared. And this function is in between the two. So now we can take the limit. Like if I look at this limit on the left side, the limit as x goes to 0 of -x squared, what does that equal? We can just use direct substitution. 0. Put 0 in for the x. 0 squared is going to be 0. And then if I take the limit of x squared, what would that be? 0. Now here's the catch. The function that we just came up with is between -x squared and +x squared. So what does the limit have to equal? 0, because it's the squeeze theorem says it has to be in between. So this limit has to be 0 because we forced it to happen. It has to be in between the two that we see. And that's it. I don't think you're going to run into the squeeze theorem too much, but it's kind of interesting to see how that works out in some examples. But it's an alternative way to find a limit for something that would be almost impossible to find the limit of any other way. So let's look at a couple last-minute examples here. This one, I think I'm going to just change this a little bit to make this more applicable. Let's make this an addition sign and this a subtraction sign right here. Let's see, would that work out? I think that'll work out okay. And let's just change the whole problem. As x approaches a -2 instead. I want to make it so that you can't just use direct substitution. So you can't put the -2 in there. So what would be a strategy that you got to remember that you should try? Okay, graphing will work. It will work to graph it, but let's say the calculator wasn't available and you didn't know how to graph it by hand. What's the other alternative? Factoring. So just remember, factoring is a process you want to look at. You rewrite this as the limit as x approaches -2. You factor the top as x plus 2, x minus 3 over an x plus 2. And if it factors real nicely and this method works, there's a factor that will drop out. So x plus 2 drops out. Then what are you back to? Direct substitution. So you just plug in the -2 minus 3, which is equal to -5. And that would be your answer to the problem. Okay, so factoring has to be on your mind when you're doing limits. So keep that in mind. The second example, we see negative exponents. We see fractions. This is where you're going to have to remember your algebra skills. So you rewrite this as the limit as h goes to 0. 3 plus h to the -1 is 1 over 3 plus h minus 1 over 3, and that's all over an h. Okay, so then what do you do next to try to simplify this complex fraction? On the top? We can do that, or we could multiply it. It doesn't really matter. I guess if we get the common denominator on the top, we would multiply these two together. So it would be 3 times 3 plus h. And what would I have to multiply the first fraction by to get that denominator? A 3. The second fraction has to be multiplied by 3 plus h. So I have to continue down here. I'll rewrite this as the limit as h goes to 0. And what's going to happen then is I have 3 minus 3. That drops out. And we get a -h. And we're divided by h, or h over 1. So to simplify that even further, when we divide by an h, it's the same as if we multiplied it by what? 1 over h. So I'm going to multiply this by 1 over h, top and bottom. So what's going to happen is these h's drop out, and you end up with a -1 over 3 times 3 plus h. Now we're still taking the limit as h approaches 0. So now we can use direct substitution then, and we would get -1 over 3 times 3 plus 0. So we get -1/9 as our limit. There's a lot of algebra here. And that's something that does show up with limits, is being able to just simplify something algebraically and then use direct substitution to calculate what that limit's going to equal. So it's kind of tricky, but that's the idea there. Let's talk about this symbol here. Does anybody know what that means? It's the greatest integer of x. Greatest integer of x, which means the greatest integer that does not exceed x. That's what that means. So if we talk about the greatest integer of, let's say, 5, what's the greatest integer that does not exceed 5? 5. Okay. Now, let's look at the graph on this, though, before I start writing these down too much here. Graphically speaking, what the greatest integer function is going to look like is at 0, it's going to be 0. And then it stays at till you get to 1, jumps up, and then it keeps going. It's like a step function, like this. So we have 1, 2, 3, 4, and then 5. At 5, it goes like this. So the question is, this is looking at the limit as x goes to 5. Is that a plus sign? Yeah, okay. So from the right, that's going to be this segment right here. What would the limit be? It's for values bigger than 5. What's the greatest integer, or the integer that's always less than like 5.2? It would still be 5, right? So that limit is 5. That's true. It's 5. If you take the limit from the left of 5, it would be like a 4.99. Then what's the greatest integer of 4.99? 4. So this should be a 4. So the limit as x goes to 5 of the greatest integer function does not exist. And then at 5.5, which is like right in the middle of this little segment, what would the greatest integer limit equal? It would just be 5. So that would just be 5 at that point. So that's just a different function, just to make you look at the limits a little bit closer and see what that looks like.